Hey everyone, Mr. Fritz here. In this video we're going to talk about vector parallelism and what the unit vectors look like in unit vector form. So let's dive right into this. For an opening problem, I have a little bit of a challenge. We want to know what is the coordinate through which vector A passes through in the unit circle. It might seem kind of tricky at first, but this is actually a good problem for what we might do later on in our curriculum. So let's actually draw this vector first. I'm going to draw coordinate plane here. Just kind of a rough sketch, and I'm going to draw vector A, and that's going to be in component form that's over 5. Let's just call it 1, 2, 3. Actually, I want to make that bigger. 1, 2, 3, 4, and then 5 would be about here, and it'd be down 2. So this is what vector A looks like. It ends about here, so it looks something like this. That's A. What I want to figure out is where this vector goes through the unit circle. So I'm kind of interested in this coordinate right there, right where this intersection is. That's what I want to know. So if I kind of imagine this thing as right triangles, really what I'm doing here is I'm scaling down my triangles. So remember, this vector is comprised of just 2 components, a horizontal component of 5 and a vertical component of 2. And this has some hypotenuse, and if I just kind of shrink down this triangle, it should have the same proportions with this little inner triangle here. Let me draw this inner triangle. So here is my inner triangle. And if I could figure out the information of the big triangle, I can scale it down and find out the information of the little triangle, which is going to get me this coordinate right here. So in order to do that, first let's find out what this side is of this right triangle, or the magnitude of this vector. So the magnitude of vector A is going to be given as the square root of the sum of the components squared. That's our Pythagorean theorem. So this comes out to be the magnitude of A is equal to the square root of 25 plus 4, which is equal to the square root of 29. So this right here, this vector A, is equal to the square root of 29. So if I want to now scale this down to fit this inside the unit circle, I need to really make my hypotenuse equal to 1. That's the goal. So scale this down so the hypotenuse is 1, since the radius of this unit circle is 1. So how I like to think about this is here's my big triangle, and right now I've got a hypotenuse of the square root of 29. I have an x value of 5. I have a y value of 2. Or I guess that should be negative 2 if I'm thinking about the actual coordinates. This is 5, negative 2. And what I want to do is I want to take all of this and I want to scale it by a factor of 1 over the square root of 29. And let's think about where that comes from. If I want to make my hypotenuse equal to 1, I'm basically dividing the square root of 29 by the square root of 29. So I have to do that to all the sides to scale this thing appropriately. So on my unit circle, let's see where that plays out. My hypotenuse would be 1, since I scaled that down. My x is going to be 5 over the square root of 29. And my y is going to be equal to negative 2 over the square root of 29. So that coordinate right here, this one that I have in green, is actually equal to 5 over root 29, comma, negative 2 over root 29. So this is pretty helpful because down the road we are going to be interested in vectors that are 1 unit long, and so we need to be able to scale down these triangles in order to do so. So hopefully that made some sense, and we'll come back to that again later. All right, real quickly I want to talk about parallelism. We know what parallel lines look like, and we talk about parallelism in vectors. Remember, vectors can kind of be moved around geometrically as we visualize them. And so when we talk about parallel vectors, two vectors are parallel if one is a scalar multiple of the other. So essentially, if I have 2 vectors, A and B, they're different sizes. Note that this has nothing to do with the size of the vectors. We just want to know if the directions are the same. So in this case, A could be a long vector, B could be a short vector. But if they are parallel, there's some way that I can multiply the shorter one or the larger one by some scalar value so that they are in fact equal. So basically what this is saying is there's some way I can lengthen or shorten one of these vectors to actually make it look exactly the same. That should make sense because scalar multiplication or multiplying by a scalar does not change the direction at all. So let's just take a look at a couple examples of this. we'll take these two vectors here, A and B, and we want to show they're parallel. So if they are parallel, that means that 12, 6 should equal some k times 4, 2. And hopefully we're seeing this right away, that if I multiply 3 by 4 and 3 by 2, I get this. So if k is equal to 3, then basically what I've proven here is that vector A is equal to 3 times vector B. And there you go. So that they must be parallel if there is a scalar that exists. So why don't you try this example? Here's a whole bunch of parallel or maybe parallel vectors, and I want you to determine which of them are parallel by seeing if there are scalar multiples between any of these two. So find pairs of these. Pause the video and resume when you're ready to check out the answer. All right, so this is it. That's my answer for these two. A and F are parallel, B and E are parallel, and C and D are parallel. So hopefully that made some sense. Let's take another look at a different kind of parallel vector problem. I want to make these two vectors parallel. And in order to do that, I have to figure out I have this missing y component or vertical component. So if we want them to be parallel, that means that 3, 4 is going to equal some scalar k times 9t. And hopefully what we're seeing here is that if I, well, I guess I could go, this might be a little confusing going this direction, but maybe I'll do it both ways, because I could also write that 9t is going to equal some scalar k of 3, 4. It really doesn't matter which one you are changing, if you're lengthening a vector or shortening a vector. We basically just want to multiply one of them by something to make them the same. So what I can do here is, if I'm using this equation, I'm thinking, well, what does k have to equal if I want to multiply k by 9 and get 3? So that means here k is going to equal 1/3. And so now I'm thinking 1/3 of t is going to equal 4. So I can kind of think about that just as its own problem. And this, hopefully the x components make sense. 1/3 times 9 gives me 3, so that's kind of how I arrived at k equals 3. So that means then that 4 is going to equal 1/3 of whatever my t value is. Multiply both sides by 3, and I get t must equal 12. Let's pretend that I put the scalar, on the other vector. And actually, if I were to do this again, I probably would, because I mean, I like to make numbers bigger rather than smaller. I think that's easier in my head to do that. Because right away I see k is equal to 3, which would make this, which would bring me to 9 after multiplying 3 by 3 here. So that means then that 9 over t is going to equal 3 times 3 over 4. And really I could just multiply 3 by both of these. So this whole vector is going to equal 9 over 12. And right away I just see that t has to equal 12. So I get to the same answer a different way. So why don't you try this example? It's very similar. You have to find out the scalar t that I'd have to multiply by either one of these if the following vectors are in fact parallel. So pause the video and give this problem a shot. Alright, here's my answer. I decided to multiply 5, negative 4 by some scalar k, and in doing so I found that t is equal to 8. So hopefully that made some sense to you. I think that's all we have to talk about for parallel vectors, so we're going to stop here, and the next video we'll talk about unit vector form.